Today's episode is brought to you by Engineering.com, a globally trusted source for engineering content. Check out this and many other exclusive videos for the engineering professional found only on Engineering.com TV today. Today's complex manufactured goods are a product of data. And data is not only imbued in the design and production processes that make things, but it is now generated by those things themselves, and forms a valuable stream of information that can be fed back in real time to engineering teams. The sheer volume of this information is itself a serious challenge to modern engineers. In our example of digital transformation in the design of an autonomous vehicle, we've explored how to control and regulate that information flood with MBSE and digital twins. Now, we'll look at how to manage the many sensors and systems connected through the Internet of Things. When we last saw our autonomous vehicle, it had rolled off the assembly line with a virtual counterpart, its digital twin. But as the real car hits real roads, how do we keep the digital twin a true representation of the actual vehicle, which is changing constantly through interactions with its environment? The Internet of Things, or IoT, is the enabler. Autonomous driving requires a suite of sensors that observe the world around the vehicle. Modern sensors and onboard processors take on a considerable portion of the computational burden of data analysis, beyond just filtering signals and rejecting noise. Much of the data from these sensors represents simple, repetitive tasks, such as lane keeping. And critical safety functions, like the ability to brake or steer quickly to avoid an accident, must be processed locally. Edge cases are relatively rare, and the easiest way to aggregate meaningful data on these cases is to work with information from many vehicles and many roads. 5G connectivity, as used to update software in real time, is an obvious solution, leveraging in-vehicle connectivity that already exists for service and infotainment systems. From the perspective of the engineering teams developing autonomous driving, the IoT devices are the sensors, and the vehicle is the device that moves them through the environment. The digital twin then has two components: the data representation of the physical vehicle and the evolving software that controls that vehicle's operation. The twins are connected to the devices in real time, a digital thread. That thread feeds data back to simulations which continually update the digital twin and MBSE model. This inevitably has product lifecycle implications, so PLM systems are ideally integrated as well. There are several approaches to autonomous driving in development globally, and not all use data generated entirely on board. Cities themselves are becoming integrated data generators. A smart city of the near future may be equipped with sensors that can communicate directly with vehicles, and vehicles may simultaneously communicate amongst themselves. The computational load on an auto manufacturer to keep the digital twin up to speed with real-world changes will be considerable. But companies that can harness this cascade of data quickly and effectively will gain a clear competitive advantage. So how do engineers harness that complexity? High-level data management tools will be used to collate and organize that data stream, and relevant data will be fed into simulation software, where artificial intelligence and machine learning come into play. The connection between real-world data and the digital twin will allow new levels of predictive analytics as well. Is a tire about to blow out? Is the transmission going to fail? Is the car in the next lane likely to swerve into you? The AI, machine learning, and simulation tools back at the information hub will be able to predict these events and direct the vehicle's operating intelligence to prevent them. With millions of connected sensors generating terabytes of data, cloud computing is the only cost-effective processing method. The accessibility and scalability of cloud infrastructure is a key enabler of digital transformation, and the ability of engineers to design intelligent devices in quantity will be closely tied to the development of cloud infrastructure. All cloud-connected devices present security issues, and security threats posed by the possibility of remote control of safety-critical systems, such as self-driving cars, can't be understated. Security, however, is a very solvable problem, and players in the intelligent device development teams consider security from the earliest point in the design phase. We've talked about the role of MBSE, PLM, simulation, digital twins, IoT, and AI as part of our hypothetical self-driving vehicle. But today, designing and building a great product isn't enough by itself. Sustainability is both a regulatory and market demand essential, and the digital thread is part of that engineering process too. That's next time on Engineering in the Digital Age.